define a radian. So what is a radian? Well, if you have a circle over here, that circle is going to have a center as well as some radius. Now, you draw an arc on the circle that is the same length as your radius. So this is your arc length, let's call this S, and let's say your arc length has the value that is equal to the value of the radius. If this case is true, then you can basically grab each of the ends of the arc length and draw a line towards the center, and you're basically going to get an angle. That angle is what we call 1 radian. So a radian is the angle subtended at the center of a circle by an arc that is equal in length to the radius. A small mass is attached to a string. The mass is rotating about a fixed point P at constant speed as shown in figure 1. So this is figure 1. This right here is the point, and this mass is going to be rotating like so about this point P. So we clearly have a circular motion over here. And I think this rope or this string is basically going to provide the tension, and that tension is going to become the centripetal force, which keeps this mass rotating around P. It says, explain what is meant by angular speed about point P of the mass. So we know what speed is, right? We know what normal speed is. It's basically your distance per unit time. So angular speed is almost the same as that, except for having distance, you have angular distance, which is basically the angles you cover per unit time. So this is just going to be the angular speed. Angular speed is the rate of covering angular displacement, angular distance per unit time, and since they're talking about point P and the mass, we can say by the mass around point P, yeah, I think that's it. So moving on to the next part, and it says a horizontal plate is free to rotate about the vertical axis to its center as shown. So this right here is a plate, this right here is an axis, and it's going through the center of this plate, and this plate is basically rotating around that axis. The mass m is placed on the plate a distance d away from the axis of rotation. So we have that mass m and its distance d away from that axis. It says the speed of rotation of the plate is gradually increased from 0 until the mass is seen to slide off the plate. And that basically means is that at first the plate is at rest at 0 speed, and then slowly they increase the speed until a point where the mass basically whoop flies off the plate. The maximum frictional force F between the plate and the mass is given by the expression F equals 0.72 W, where W is the weight of the mass m, and the distance d is 35 centimeters. So I'm just going to cut this, and I'm going to write 0.35 meters over here because I don't like my values in centimeters. Okay, so what's going on over here? Well, we know there's a frictional force, and I want to ask you guys, do you know where that frictional force will be pointing? So if I just draw the free body over here, that right there is the center, let's call it C. That right there is the mass m. What are the forces acting on this mass m? So clearly this mass is going to have a weight that is going to be acting downward. The weight is W, and then that weight is basically canceled out by this normal force since it's sitting on a plate, so that plate is providing a normal force. And then where is that centripetal force going to be pointing? Well, this mass is going to be rotating, and it wants to fly off. So it's going to fly off the plate, and the centripetal force basically opposes your motion. So if you want to slide off the plate, the frictional force, this maximum frictional force, this basically wants to keep you on the plate. Frictional force is a force that opposes your motion. So it's going to keep you on the plate, and since this is a circular motion, it's going in the center, so this centripetal force will basically try and keep you on the plate so that you don't just fly off and go whoop. This right here is your frictional force. I'm going to write it with a small subscript F so that you know we're talking about a frictional force. Now, the key realization over here is that this frictional force is actually related to the centripetal force. We know what the centripetal force is. It's basically a type of resultant force, okay, and it acts towards the center. So it acts towards the center. I'm just going to write C over here. And in this free body diagram, there's only one force that acts towards the center. That is the frictional force. So the centripetal force is equal to the resultant force acting towards the center. In this case, we only have one force that is acting towards the center, that is the frictional force. And so the centripetal force is going to be equal to this thing right over here. And we know what this thing is. This thing is basically 0.72 W. Okay, moving on to the next part, it says determine the maximum number of revolutions of the plate per minute. Okay, that's a lot of words. What does this thing mean? So it says maximum number of revolutions per minute. Now, all of these words, these fancy words, they're basically here to confuse you. This just means maximum revolutions per minute. Now, what is revolutions per minute? What if I tell you that you have a car moving at 60 kilometers per hour? or 60 meters per second. You obviously know we're talking about speed, or we're talking about velocity. So in the same way, the angular speed has two units. We know it in its radians per second form, and we know it in its revolutions per minute form. Over here, this thing right here is a fancy way of saying omega, or the angular speed, and the maximum word is basically asking you for the maximum angular speed. So it basically simplifies to determine the maximum omega, or the maximum angular speed, for the mass m to remain on the plate. And what does this mean? Well, they told you that you have a plate, and it's going to start at rest, but then it's going to get faster. And so it gets faster, 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 faster. But they're asking you for the maximum amount of speed that you can have so that the mass remains on the plate. Now, what happens as you get faster and faster and faster? Well, as you get faster and faster and faster, you're more likely to fly off the plate. So at first, when you're moving slowly, a tiny amount of the frictional force is enough to keep you in that circular motion, or keep you onto that plate. Then as you get faster, more force is required. As you get faster, more force. And then as you get faster, even more force. However, we have a cap. We have a cap on the amount of maximum force that you can have, and that cap is 0.72 W. So this is the maximum force that you can have. Okay? If you go faster than how much this force can pull you in, then what's going to happen? You're basically going to fly off the plate. So what do we need to do over here? We basically need to decide the maximum omega based on this maximum centripetal force, because otherwise, if you exceed that certain omega, or you exceed a certain speed limit, then this force right over here is not going to be enough to pull you into that circular motion, or hold you on the plate, and you're just going to fly off. So what do we need to do? We need to find our omega based on the centripetal force, or the frictional force, you can call it whatever you want to call it. In this example, we've already seen that the centripetal force is the frictional force, so it doesn't really matter. So we're basically trying to find omega based on this centripetal force. And so how do we do that? Well, you can go ahead and tell the mathematics that you need to find omega based on the centripetal force. And what that means in mathematics is that you basically need an equation that has omega and that has the centripetal force, because then you can relate these two, make omega the subject, and use this maximum value of centripetal force that you have to find the maximum value of angular speed that you can have, so that you remain on the plate. Remain on the plate. And so how do we do that? Well, we know we have an equation, centripetal force equals to m omega squared r. This equation has omega, this equation has the centripetal force, so we can relate these two over here. Now, I am going to input the value for this maximum centripetal force that has been given to us in the question, that is 0.72 W, and the mass in the question is given to us by a capital letter M, so I'm just going to write that, omega squared r. Now, the problem over here is I need to find omega. Omega is unknown, that's what I need to find, but I have two more unknowns, the m and the w. I have not been given those in the question. I have been given the distance r of the mass from the center. So I know that is 0.35 meters, but I don't know my w and I don't know my m. So I need to get rid of those, because I cannot solve this equation if I have three unknowns. That's not going to happen. What do I do? Well, I know that my w is equal to mass times g, and that's the only way to get rid of these unknowns, this w and this m. If you don't figure this out, that you can replace the w with an mg and then cancel out the m's, you won't be able to solve this problem. So that's basically the key trick over there, that you need to realize that w, the weight of the mass, is basically equal to m times the gravitational acceleration. Once you know that, you can basically remove the m. You don't need it anymore, and now you're just going to be left with 0.72 g equals to omega squared r, and now you can just go ahead and make omega the subject. So that's going to be 0.72 g over r, send the square to the other side, that's going to become square root, and now you can just plug the values in. So this is going to be 0.72 times 9.81 divided by 0.35, and this, I believe, is 4.49 radians per second. But you don't want to plug this value in, because they asked the value to be in revolutions per minute. So whenever you want to convert from radians per second to revolutions per minute, what you do is you basically take your value in radians per second, you multiply it by 60 divided by 2 pi. And that's basically going to give you, I believe, it's approximately going to give you 43 revs per minute. So this right here, 43 revs per minute, that right there is the number of maximum revolutions per minute that is possible. Now remember, what's going to happen if you exceed this number? Well, the moment you exceed this number, the centripetal force, the maximum centripetal force, this thing 0.72 W, this won't be enough. So this won't be enough to keep that mass m in the circular motion. And so if the mass gets faster than this, if the mass gets higher omega than this, if you keep on speeding up the plate, then the mass is just going to fly off. So what did we do again? Well, we found the omega, the maximum omega that was possible with the maximum centripetal force that we had available to us. That's all we had to do in this problem. So we go on to the next part, and it says that the plate in B, part B, is covered when stationary with mud. So Justin explained whether mud near the edge of the plate or near the center will first leave the plate as the angular speed of the plate is slowly increased. So you got the plate, they cover this thing with mud when it's at rest, and then they spin this thing. And then they're saying, as we're making it faster and faster, tell us, will the mud on the edge leave the plate at first, or will the mud near the center of the plate will leave the plate at first? And well, it's basically going to be the mud that is at the edge of the plate. The reason for that is because if this is the center of rotation, let's call that C, the further you get away, so let's say there are two things, one's over here and the other one's all the way over here, this thing is going to require less centripetal force to keep it in the circular motion around center C, whereas this thing is going to require way more centripetal force, to keep it rotating about the center. So the further away you get, the larger the centripetal force is required. So it's more likely for this mass to fall off first, because it's going to require a much larger force than this mass. So the answer is the mud on the edge leaves the plate first, because it requires a much greater centripetal force than the mass at the center. We've already discussed what the radian is, so we're not going to be doing that. But we move on to the next part, and it says a stone of weight 3 newtons is fixed using glue to one end P of a rigid body CP, as shown in figure 1.1. So this is figure 1.1. That right there is a stone, and it's fixed to this rigid body CP with glue. And I think the radius of this is 85 centimeters, so I think this thing right over here also has to be 85 centimeters, but I'm just going to convert this to meter and write 0.85 meters over here. So it's basically this stone is going in a circular motion. We can clearly see that. In the next part, it says that the rod is rotated about the end C, so that the stone moves in a vertical circle of radius 85 centimeters. We already know that. The angular speed, omega, of the rod and the stone is gradually increased from 0 until the glue snaps. The glue fixing the stone snaps when the tension in it is 18. So the tension in the glue is 18, and that's when it snaps. Okay, perfect. For the position of the stone, at which the glue snaps, we have to first, on the dotted circle of figure 1.1, mark with letter S the position of the stone. So at this point, at this position, we need to basically mark with the letter S the position of the stone. So the position of the stone where the glue snaps. So where is that most likely to happen? If you've ever had a string and you've attached it to something and then you've rotated it about a circle, then what you would have found out is that the string feels the lightest when it's on top, and it feels the heaviest when it's at the bottom. So the place at the bottom, that's when the string feels the heaviest. And so that is most likely where the glue snaps. This is the lowest point. That's the most likely point where the glue snaps. And so that's going to be right over here, the point S. I think we were supposed to mark it with the letter S. Yes, that's the letter S. In the next part, it says calculate the angular speed omega of the stone. So for this point, I'm just going to draw another diagram for this point. This right here is the circle. That right there is the center. Let's call it C. And that right there is the mass, or the stone. And what's happening over here is basically, at this point, this mass basically snaps. So I'm just going to make a free body diagram so that I can explain it to you guys what's actually going on over here before I answer the question. So this stone, or this mass, is going to have a weight that is given to us as 3 newtons, as you can see up over here. This was given to us in the first sentence as 3.0 newtons. Okay, then it has another force. It was the strength of the glue, or the tension in the glue when it snaps, and that tension is 18 newtons. That's acting upwards. So that's what's happening with this stone so far, right? Nothing too fancy. Two forces are acting on it. That's all that we got over here. Now, we need to calculate the angular speed of the stone. And this over here is the setting that we have. So this right over here, this is the setting that we have. Now, how do we do this? Well, you clearly know that the stone is moving in a circular motion. So if you want to find omega, of course you're going to use the equations for a circular motion, because you're not going to use the kinematic equations, or you're not going to use the harmonic equations, or you're not going to use the projectile motion equations. It's clearly a circular motion, so you need the circular equations, and you want to find omega. So how can you find omega? What's the equation that allows you to find omega? Well, that's basically Fc, centripetal force, equals to m omega squared r. That's the equation in circular motion that allows you to find your omega. Now, they gave you this tension 18 for a reason, and that's because so that you can go ahead and calculate out this centripetal force. Now, what is a centripetal force? Centripetal force is basically a resultant force that acts towards the center. And over here, what force is acting towards the center? Well, it's clearly the 18 newtons force. Clearly the 18 Newton force. But is that 18 Newton force the resultant force? You got to ask yourself that. Is it? Well, it's clearly not, because there's a 3 Newton force that acts in the other direction. And so it's clearly not the resultant force. So to find out that resultant force, you basically have to subtract that 3 Newton force that is in the opposite direction. And so you realize that you get a 15 Newton force that is going to be pointing in the center. And this right here is your centripetal force. It's not only the resultant force, but it also acts towards the center. So this is your centripetal force. I need to find W, so I'm going to rearrange the equation for that W. And that's just going to be Fc divided by mr square root. And now you can go ahead and put the values in. So it's going to be Fc is 15, right? The mass is going to be 3 divided by 9.81 times the radius. The radius is 0.85. They already gave that in the question. 7.596. I'm going to round this off to 7.6 rads per second. So that right there is 7.6 rad per second. That is going to be my angular speed omega. We already did what a radian is, so we're going to leave that one off. And we're going to move to the next part. It says why one complete revolution is equivalent to an angular displacement of 2 radians. And what they're asking is they're basically trying to ask you guys why, when you go around a circle, why is this, why are the angles you cover equal to 2 pi radians? And that basically comes out of this formula, S is equal to r theta, this formula. And what you need to understand is that for one revolution, you basically go around the circumference of a circle. So if you're standing over here and you go around a circle like this, the length you've basically covered, all of this circumference that you've basically covered, the formula for this is 2 pi r, right? So your S is basically your 2 pi r. The distance you covered is basically 2 pi r. It's the circumference of the circle for one revolution. And so you can basically substitute that. So you can substitute the S in r theta, and then you'd basically get 2 pi r equals r theta. So again, we're doing this for one revolution, okay? So you just cancel the r's, and you realize that the theta you get, or the angular displacement you get, that's just equal to 2 pi. And we call this radians. This is just 2 pi radians. So you can go ahead and write it over here that for one revolution, for one rev, S is equal to 2 pi r. Therefore, S equals r theta becomes 2 pi r equals r theta. And you can say on simplifying, theta becomes equal to 2 pi. And then you can say hence shown. So moving on to the next part, and it says an elastic cord has an unextended length of 13 centimeters. One of the end of the cord is attached to a fixed point C. So you had a cord, and it had a length of 13.0 centimeters. You attached one of these ends to a fixed point, point C, and then you hung a mass of which had a weight of 5 newtons, and so you basically got this thing over here. The cord extends to a length of 14.8 centimeters as shown in figure 1.1. So that's what's basically going on over here. And now see, when they say the cord extends when you attach a weight and it has an unextended length, they're basically hinting to you that this problem is going to have elements of the deformation chapter or the Hooke's law chapter, because that's what we see in that chapter, right? You have a spring or some string and it has an unextended length, and you attach some weight to it, and then it becomes extended. And then there's a force, there's a spring constant, there's an extension. In the same way, they've kind of already hinted to you that it's a cord that extends, and you apply a weight, and so there's this extension in the cord. And so what I want you guys to do is just right off the bat go ahead and find the constant K, the spring's constant for this cord. It's going to be a cord constant. Just go ahead and find that off right in the start, because I know they're going to make you use that in the end, because otherwise why would this cord extend? Why would this be an extension problem? So they're specifically trying to show you guys that this is a deformation problem. It's a Hooke's law problem. So you have a force, and you know that force is going to be equal to Ke or Kx, right? This is the Hooke's law problem. And the force that you apply over here to this cord is basically 5 newtons. And the extension that you get, I'm just going to write that in meters. So 14.8 centimeters is going to be 0.148 meters, and then 13 centimeters is just going to be 0.13 meters. And you subtract these two, you're just going to get 0.018 meters. So this thing right here is going to be 0.018 meters, and you can make K the subject. You're going to get this thing right over here, which is K. And of course, this is newtons per meter. Okay, so we just found the K for the cord. Okay, moving on to the next part. Says the cord and mass are now made to rotate at a constant angular velocity, at a constant angular speed, omega, in a vertical plane about C. So that fixed point that we had, now that mass is made to sort of rotate about that point C. So it's basically doing a circular motion right now. It's a circular motion. And of course, if you have elements of circular motion, you're obviously going to be using the circular motion equations. Centripetal force equals to m omega squared r. Centripetal force is equal to mv squared over r. Okay, those equations. So it says when the cord is vertical and above C, its length is unextended, length of 13 centimeters as shown. Now, what does this mean? So we know that this mass was basically hanging like this, and then they basically caused this system to rotate about that central point, point C. And what they say is when this mass is right above this point C, what's happening is that basically this cord is not extended. It's at its original length, 13 centimeters. And what does that even mean? That basically means that there is no tension in the string or the cord. And why is that? Well, because if you look at a spring, or if you look at anything, which it's when it's in its original length, there's no force in the spring, right? But when you basically apply a force to it, there's some extension, and so there's some force. But over here, the cord is at its unextended length. It's in its original length. That means it's not being stretched. So if the cord is not being stretched, obviously it's not going to have a tension. So this thing basically means there is no tension in the cord. Being at its unextended length means there's no tension in the cord. There's no force in the cord. That's what it means. It's a loose cord. It's a loose cord. I don't think we have to do anything with figure 1.3 right now since they haven't mentioned it, so we're just going to go to the next part. And it says, show that the angular speed, omega of the cord and the mass is 8.7 rads. So we're supposed to find omega. How do we find omega? We already know this thing is going in a circular motion, so we can use the equation of the circular motion, and we know that through that equation we can find omega. So we're going to use Fc equals m omega squared r. Now, what is the centripetal force going to be? Well, we know that the centripetal force is basically a resultant force that acts towards the center, right? So if we just draw a free body diagram, over here to figure out what are the forces that are acting on this mass while it's in its circular motion, we can understand what our centripetal force is going to be. So obviously this mass right over here, I'm actually going to remove that string. Let's remove that cord. We are going to have its weight that's going to point downwards. Obviously, the weight always points downwards. So it's going to be pointing towards the center because this mass is directly above C. Above C. That's what they told us in the question. Now, is there another force that is acting on this mass? No, there shouldn't be another force. We're not talking about air resistance. This isn't attached to anything else. It is attached to a string. It's a loose string that this mass is attached to. But we know that that string is loose, that cord is loose, and so that means there's no tension or force in the string. There's none of that stuff. So the only force that is acting on this mass is its weight. And so is it pointing towards the center? Yes, it is pointing towards the center. So there's one force, there's one resultant force, right? There's one resultant force, that is the weight. Resultant forces are also known as unbalanced forces. So there's one resultant force, which is the weight, and it's also pointing towards the center. So that means that in this case, the centripetal force is basically our weight. It's provided by the weight. The centripetal force is provided by the weight. So what we can do over here is we can basically substitute the weight over here for centripetal force, and we actually know what the weight is. So the weight is 5.0 newtons. I believe that was the weight that was given to us in the problem. Yes, it was 5 newtons. So this is going to be our force, and we are going to have our mass is going to be 5.0 divided by 9.81. Then this is going to be the r is going to be the distance that the mass is away from the center, and this was 13 centimeters because that's how long the cord is at this point. And I'm just going to convert that into meters and write 0.13 omega squared. So now if I just solve all of this out, this is just going to be 5 divided by 9.81 times 0.13, and I basically do this, so I basically get 981 over, I believe it's 13, is equal to omega squared. I take the square to the other side, it becomes a square root. And so my answer is going to be 8.68, which could be rounded off to 8.7 rads per second. Moving on to the next part, says the cord and mass rotate so that the cord is vertically below C. Okay, it's vertically below C now. As shown in figure 1.3, calculate the length of the cord, assuming it obeys Hooke's law. So they've already told you, see, I told you this was going to be a Hooke's law problem because that's why we had extension and original lengths in the first place. Now, what they're basically saying is that you have this figure 1.3, and what's happening is that as this mass rotated, it was over here, vertically above C, and then it basically rotated, and now it's vertically below C. And now this cord is actually in extension. It has some new length L. We don't know what that length L is, but it's some new length L that we have to find. So we are going to find this, but before we do that, some of you may be like, well, why is that length not 14.8 centimeters? Well, the answer to that is because you may just be like, okay, well, this over here, the mass is vertically below C, and it's 5 newtons, it's 5.0 newtons acting downward, so shouldn't the length L just be 14.8 centimeters? Well, it should be that if it was in rest. The thing is, it's not in rest right now. It's moving, okay? It's moving in a circular motion. And so what that circular motion does, that circular motion is actually going to have some effect on the forces that are acting on this wire. So that effect is basically what's going to cause L to be a different value than 14.8 centimeters. If the system was in rest, then yes, it would have been 14.8 centimeters. But since it's a rotating system, it's rotating in a circular motion, that's why the L is not going to be equal to 14.8 centimeters. And so we have to actually take that circular motion into account, and based on that circular motion, we have to find what L is, and that's exactly what we're going to do. If I just draw my system over here, so this right over here is my C, that right there is my mass M. Now, of course, there is some tension in the string at this point. Why do I know that? Well, because there is an extension. That extension causes the cord to be stretched and get into some new length L. The original length was 13 centimeters. Now it's some length L. I don't know what that L is, but due to that extension, I know that there's going to be a tension in the string. There's going to be a tension in the cord. And the weight is basically going to be acting in the downwards direction. The string is obviously going to be in the opposite direction. It's going to point upwards towards C. The tension the weight is going to try and pull on the string. The string is going to be like, no, don't pull on me. So the tension is going to act upwards towards C. Now, why am I drawing this? Why am I drawing a free body diagram? Well, because I know this is moving in a circular motion. And if I know my forces, then I can basically calculate my centripetal force. So I'm just going to do that. Now, my centripetal force is equal to m omega squared r, right? This is one of my equations. This is another equation, Fc is equal to mv squared over r, but I don't know what my v is, so I'm just going to ignore this equation. There's no point in using this equation because I don't know what v is. I haven't calculated v. I can do that if I want to, but I don't need to. I can just use this equation and work with this. So first of all, I know that the centripetal force is basically a type of resultant force that acts towards the center, I have two forces at this point that are acting on this mass. One of them is the tension. So this right here is the tension that is pointing upwards towards the center. But is that the resultant force? I know it does act towards the center, but it's not the resultant force. Why? Because there's some weight that's acting in the opposite direction, and it's basically going to cause this tension to reduce. It's basically going to cause the overall resultant force to reduce. The tension is going to stay the same, but the overall resultant force is going to reduce. This weight is going to cancel out some of the effect of that tension. So the resultant force is the tension is acting towards the center, but it's not the only resultant force. So how do we find the resultant force? Well, if the tension is acting towards the center and the weight is taking some effect of the tension away, then we just need to subtract the weight from this, and that is basically what our centripetal force is going to be. Now, whatever you subtract this, and whatever the final answer you're going to get, that is basically going to be your resultant force that acts in the center. And since it's going to be this specific force, we know that we have a special name for it that we call the centripetal force. So I can basically go ahead and put that in this equation, this Fc is equal to m omega r squared. My centripetal force is, I already know it's going to be tension minus the weight, and the weight is 5 newtons. It's going to be equal to the mass times the omega squared, and this time that r, that distance that this mass is away from that center, that distance is L. So I'm just going to put NL over here. Now the problem is, I need to solve for L, but here's the problem. The problem is that I don't know this. So I do know my mass, I do know my omega, I don't know what my tension T is. They don't tell me the tension. So I cannot just solve this equation for L. I cannot just make L the subject and solve out this equation. I have one equation and I have two unknowns. So this is not going to solve. But you know what is going to solve? If we had another equation with these two unknowns, then this would be a solvable system. If we had another equation with this unknown and this unknown, two equations, two unknowns, that we can solve using simultaneous equations. So that's exactly what I'm going to do. And if you think about it, and you're like, okay, how do I get tension? If I want to find tension, how can I get tension? There is actually a way you can get tension. And that way is basically, you know, from your Hooke's law or your Springs chapter, they even tell you in the question that assume the chord obeys Hooke's law. So it's the formula for Hooke's law is basically force is equal to KE, right? And you know K because we just found that out in the first step. That's what I did. I knew it was going to be an extension problem. I know it was going to be a deformation problem. So I went ahead, I found out my K. I don't know my extension, and I don't know my force, but I know what my force is, right? My force is basically the tension that's in the chord, right? That tension is my force. So I can replace the T over here. Now the tension in the chord is dependent on the K, which is 5 over 0.018 Newton meters. I just found that out in the first step. And E. Now I don't know what my extension is, but I know that extension is equal to the final length, which is L, minus the original length, which in meters is 0.13 meters. So this right over here is how I can find my tension. And if I realize that there's a mathematical relationship over here, and that mathematical relationship is basically that now you have two equations. This is your first equation, this is your second equation, and now you have two equations, two unknowns. Using this system, now you can actually go ahead and you can solve for L, because you need to find what L is. So what I'm going to do is I already know that my T is equal to all of this stuff. What I'm going to do is I'm just going to substitute this in place of T over here. So this is basically going to be 5 over 0.018 L minus 0.13 minus 5 equals to m omega squared L. Now remember, we're trying to solve for L. So what I'm going to do is I'm just going to get all the L terms on one side of the equation, all of the other terms on the other side of the equation. So this is going to look something like 5 over 0.018 L minus 5 times 0.13 over 0.018 minus 5 equals m omega squared L. Okay, and let's just solve all of this. So you solve all of that, you're basically going to get 5 over 0.018 L minus 41.111 equals m omega squared L. Now we are going to get all the L terms on one side of the equation, so this is just going to be 5 over 0.018 L minus m omega squared L is equal to 41.111. And now we can just solve this out, but before we do that, I would like us to take this L common. So if we take this L common, we're basically left with 5 over 0.018 minus m omega squared is equal to 41.111, and then we can just divide all of this over there onto the other side. So this is basically going to be L equals 41.111 divided by 5 over 0.018 minus the mass, which is equal to 5 over 9.81, the weight divided by the gravitational acceleration, times the omega squared, 8.7 rads squared. And you put this entire thing in your calculator to be equal to 0.172, right? I rounded this off, and it's going to be in meters because I converted all of my units to meters when I was initially about to solve this problem, so I'm going to get the answer L in meters as well. But they want the answer in centimeters, so this, I believe, is just going to be 17.2 centimeters. I just write that original length, 17.2 centimeters over here. So we got a problem over here, and it says a large bowl is made from part of a hollow sphere. A small spherical ball is placed inside the bowl and is given a horizontal speed. The ball follows a horizontal circular path of constant radius as shown in the figure 2.1. So basically this is a bowl, and inside the bowl there's this ball, and it's doing circular motion. All of that has been given to us by the question. And the radius of that circular motion is basically 0.14 meters. I just converted this radius to meters. In the next part it says the forces acting on the ball are its weight and the normal reaction force R of the ball on the ball as shown in figure 2.1. So this is the normal reaction force, which is like this. It's acting in this direction. Then we got the weight of this ball acting downwards. Now, some of you may be like, okay, why is this not the reaction force? Shouldn't this be the reaction force? Well, no, that should not be the reaction force. And the reason for that is because the reaction force is always perpendicular to a surface. And so if this is the wall of the bowl, this ball is going to be something like this. What I want you guys to do is I want you to realize that you have a curved path. And that curved path, if you draw a tangent to any point, right? Let's say this point, this is the tangent to this point, then the perpendicular is basically going to make a 90 degrees with this tangent, and that's what's happening over here. There's this point at which this ball is in contact with this wall of the bowl, and so the normal reaction force is basically going to be perpendicular to this point. That's why we don't have a normal reaction force acting in this direction. Now it says that the normal reaction force is at an angle theta to the horizontal. So this right over here is the ball, right? And it's like this. And they basically drew an axis over here. So this would be the horizontal, this would be the vertical, and the R, the reaction force, is sort of at an angle theta to the horizontal. So this is the horizontal H, that is the reaction force, and it's theta from the horizontal. It says by resolving the reaction force R into two perpendicular components, show that the resultant force F acting on the ball is given by the expression W is equal to F tan theta. So what they want you to do is you can see that there's this force R, and if you draw an axis over here, if you draw an axis like so, this is the vertical, this is the horizontal. What they want you to do is they have this force R. They want you to break it into its vertical component and its horizontal component. And the reason they say perpendicular is because obviously the vertical and horizontal have a 90 degrees angle between them. So it makes sense that they're both going to be perpendicular. Now, how do you do that? Well, you have an angle theta, so you're going to obviously use some trigonometry and split this angle into two parts. Now, let's do it over here. So if we split this into its vertical component, so vertical component, that's basically going to be equal to, let's see. So it's basically something like this. This is R, this is theta. This is going to be the horizontal component. This right here is going to be the vertical component. This one right here is what we're trying to find. That right there is theta. So what we're going to do is when we're trying to find out the vertical component, it's going to be sine, I believe we're going to use sine theta is equal to perpendicular over hypotenuse, and then we're going to make perpendicular the subject. So that's just going to be hypotenuse times sine theta. And we already know that the hypotenuse is equal to R. That's what R is. So we can just input that in here. And so the vertical component or the perpendicular component is equal to R sine theta. Now we can go ahead and find the horizontal component. And that is basically going to be equal to, I believe that is going to be equal to cosine theta is equal to base over hypotenuse, and we can go ahead and make base the subject. So this is going to be h cos theta, and I'm actually going to do some of the working over here. So the horizontal component or the base is basically equal to r cosine theta. Now what they're trying to ask us is they're basically trying to say that we need to give an expression which says that the weight W is equal to F tan theta. Now what is F? F is the resultant force acting on the ball. And we need to show that the resultant force acting on the ball is basically related somehow to this equation, which is W, and that is the weight of the ball, equals F times tan theta. Now let me see what we can do over here. So we need to somehow find the resultant force. Let's do that. We've done the first part. We've split it into its vertical components. Now let's figure out what the resultant force is going to be. So we have a system that's something like this. It has an R vertical, it has an R horizontal, and then it has W down here. That's the weight. So this is R horizontal, this is R vertical. So this is equal to R sine theta. This is equal to R cosine theta. This right here is the resultant force because it's going to be providing it's directed towards the center, right? The ball is going to, when it's covering its horizontal distance like so, right? It's going to cover its horizontal circular motion. There's going to be a center there, and that thing right over there, that's basically R cosine theta, or the horizontal component of R. And so the weight is going to be downwards like that, and then it's going to be balanced by the vertical component of R. So the weight is equal to let me find out. Wait, let me see what I can do over here. So the resultant force F. Well, the resultant force, I think this is the resultant force, and they want us to call this thing F. I think that's what they're trying to do over here. So maybe we are going to call this F, okay? And so now we sort of have something like this, where this right here is our weight. That right there is our resultant force F. We know that there was an angle over here that is equal to theta. Right, I'm ignoring R for a second. I'm just trying to figure this out. And so the vertical component of this F has to cancel out the weight, because the ball isn't moving up or down, right? So the ball is balanced in its up and down motion. It's only moving in a circular path, and it's at a level, and it's not going up or down. It's at that level, and it's just covering a circular path. So that means the only resultant force it must have is one that is directed towards the center. And so far, it's this component of the normal reaction force, the r cos theta, that is providing that centripetal force or that resultant force. So I have something over here. I've basically drawn a new diagram. I've called that r cosine theta my F. And what I'm supposed to be seeing over here is that there should be a vertical component of this thing, of this force F, and that should balance my weight W. And let me just do some trigonometry over here, see if that works. So this thing right over here is F, that right there is theta, this right here is some vertical force, And I'm having a problem over here actually doing this. Can't really figure this out. So if that is my weight, show that the resultant force F acting on the ball is given by the expression F tan theta. Now, they're calling something, huh. Uh, well, I know that this W is equal to R sine theta. That's something I know. And they want me to get rid of R. I know that there is no R in the expression, right? That expression that I have, there's no R in there. There's an F in there. So I need, maybe if I get rid of this R, I will be able to do something meaningful here. I know this right here is my resultant force. So my resultant force is equal to R cosine theta. Can I do something with this now? Can I do something with this? So my resultant force F is equal to R cosine theta. And that basically means that if I make R the subject, I'm basically going to get F over cosine theta. And yes, that's actually what I have to do. So this is what was going on. I'm just going to explain it to you guys what was happening. So there was that ball right over there, and it's at this bowl. It's moving in this bowl in a circular motion like this. I'm not drawing the entire bowl, but you guys get the idea. And it's just covering this it's just covering the circular motion about the center C. It's not going to go up. It's not going down. They've already told us that in the question. It's covering a horizontal circular path, and it's just at that's that line. So it's not going to go up or down. And we know that the vertical component of R is going to balance that weight, because if they're not balanced, it's either going to go up or it's going to go down. So they both have to be balanced. So they're both balanced. That's checked. So we get this equation, W is equal to R sine theta. But we don't want that R. They want to have that F in there. So we need to find out what that F is. And that F is basically this resultant force, because that's the only resultant force in this situation. So that force, we know what that is. It's basically the horizontal component of R. And that's the horizontal component of R is basically R cosine theta. So what we need to do is we just need to get rid of this R over here, and we can use this other equation to get rid of that R. So this R is basically, if you make R the subject, it's basically going to be F cosine theta. And so we're just going to put that over here. So that R is F cosine theta times sine theta. And we know that sine theta divided by cosine theta, this is going to be F sine theta divided by cosine theta. We know that when you divide sine theta by cosine theta, you get tan theta. So this W is basically going to be equal to F. The cosine and sine are going to become tan theta. And so hence I have proven that my W, that my weight, is equal to F tan theta. Okay, moving on to the next part, it says state the significance of the force F for the motion of the ball in the bowl. Now the motion is of course a circular motion. And so the significance is that the force F basically provides the centripetal force. The centripetal force for the ball's circular motion. For the ball's circular motion. And it makes sense, right? Because that's the only unbalanced force that is in this direction pointing towards the center of the circular pad that this ball is covering. And if we didn't have that force, there wouldn't be a force that provides a centripetal force. And without a centripetal force, we would not have a circular motion. Moving on to the next part, says the ball moves in a circular path of radius 14 centimeters. We're going to get rid of that. It's going to be 0.14 meters. And even in the answer, you can check they have the answer in meters per second. So we're just going to convert this into meters. For this radius, the angle theta is 28 degrees. Calculate the speed of the ball. Okay, so it's moving in a circular motion. We can use the equation for a circular motion, which is basically Fc is equal to mv squared r. We're not going to use m omega squared r because we're not trying to find omega. We're trying to find the speed. We're not trying to find the angular speed. So this is the equation we're going to use. Now we know what that centripetal force is equal to. We know that it's basically equal to r cosine theta, and we also know that it's equal to. We also know that it's equal from this equation. From this equation, W is equal to F tan theta. We also know that this force is equal to W over tan theta. Now the reason I cannot use this equation is because I don't have the R. So without that R, I cannot calculate this. I do have a theta, but I don't have the R. So I won't be able to find my centripetal force. But using this equation, I actually can go ahead and find my my resultant force, because I do know what the W is going to be, and I do know what my theta is. And I think they've given me the W in the question. If I can just go over here and check that out, I think I was given something. And I'm trying to see. Okay, so they didn't give me the weight for the ball. That's sad. That's actually really sad. Do I need the weight of the ball though? How am I going to approach this if I don't even have the weight of the ball? Wow, that's actually really sad. Okay, what do I do over here now? I'm stuck. Give me a second. Give me a second. Hold on. Give me a second. What do I do? So it says the ball moves in a circular path. Calculate the speed of the ball. Calculate the speed of the ball. Okay. How do I do that for the radius 28? Okay. Okay, what if? Okay, so I don't have the R and I don't have W. So this is a mathematical problem now. I have a lot of unknowns. I don't want that many unknowns. I need to get rid of these unknowns. So what's one way of getting unknowns? Well, there's one way of getting rid of unknowns, and that's basically through cancellation. So I think my best bet is calculation, and if I'm trying to find my centripetal force, I will need to cancel out the unknowns. Cancel out the unknowns. I don't have an R. I don't have an R. I don't have the weight. I hope I'm going to check again because I don't want to be mistaking this. Okay, I don't have the R. That's perfectly fine. So I know that my weight is equal to my F force times tan theta. Now, if I can, now here's my plan. I know what F is in terms of R. I have an equation for that. I know what my weight is in terms of R. So if I express these both in terms of R, I can cancel the R on both sides of the equation. Both sides of the equation. And I'll show you guys how I'm going to do that. So I'm going to have my W. I know that there was a downward force of W, there was an upward force of R sine theta. So this W was basically equal to that thing. So I'm going to express my W in terms of R, and if my W is pointing downwards, then this is, let's say that r is basically going to be in that opposite direction, and so I need to account for that direction as well. I can't just say that, oh, this w equals to that r sine theta, right? Because they're in the opposite direction. So either this has to be negative, or if this is positive, then that has to be negative, because I do have to take care of the directions. Or you guys can basically see it this way, that the sum of w and the sum of r sine theta needs to be equal to 0, because otherwise the ball wouldn't be balanced. It would either move up or down. In that case, you add these two things up, and you should get 0. So if you rearrange this equation for w, you're going to get w is equal to negative r sine theta. And in the same way, I know that my resultant force is basically the horizontal force, or the horizontal component of that r. And that's basically r cosine theta. So this F is basically just r cosine theta. So what I'm going to do is I have this equation, w is equal to F tan theta. I'm going to replace these two things. So the w is going to be minus r sine theta. The F is going to be, it's going to be r cosine theta. And then that tan theta is just going to be over there. And now what I can do is I can cancel out the r's on both sides of the equation. So now I have negative sine theta is equal to cosine theta tan theta. But oops, I just have a problem now. I can't really find anything now, can I? Okay, okay, this is not good. This is actually really bad. No matter what I do, I'm unable to calculate my centripetal force. Maybe I'm supposed to use something else. I can't use this because this has no value for F. I need to find F. This doesn't have an F in it, so I won't be able to find enough. So this is actually a tricky problem, and I'm trying to figure out what I can do with this thing. So let me just see what I have again. Come on, it does have, and why would they make me create an equation? That just doesn't make sense. I have to use that equation. They made me create this equation for a reason. I have to use it somehow. So how do I have to use it? That's what I need to think. That's what I need to figure out. This is a bit complicated, but we're trying to sort of figure this out. Huh. Well, I didn't expect to be stuck like this, so this is definitely not good. That right there is an upward force. So that is a horizontal force. That right there is an upward force. Am I supposed to even use this equation? Maybe I'm not supposed to find my centripetal force. Maybe the centripetal force is why I'm having all of these problems. What else can I do? Well, I know if I have a circumference and something's moving in that circumference, like so, I can base, and I know the radius of this circular path. I can just find out the distance this thing covers, 2 pi r. That's going to be found by 2 pi r, and then I divide that thing by the entire time it took, and that's going to give me my speed as well. That's basically distance over time, right? But I don't have the time, and I don't think I need to use the time in this problem. So how do I just use this this data, and how do I just make work with this? Like that almost seems impossible. I don't even have my mass. Wait. Oh, I actually know what I'm supposed to do. Okay, I think I figured it out. So that's the reason why they made me. Okay. Guys, so this is what we're supposed to do. So we have we have w, the weight, equal to F tan theta. We don't know the mass for a reason. If you don't know the mass, we can cancel out the mass. So what we're going to do is we have w is equal to F tan theta, and we know that this F is basically our resultant force. So this is also going to be our centripetal force, because it's a resultant force that points in the center. So in other words, this is our FC. This is our centripetal force. Now, if we make this the subject, this is just going to be FC is equal to w over tan theta. And the trick over here is that you're not supposed to know the mass, because you're supposed to express this as mg, and then you can go out and cancel the masses. That's what we're supposed to do. So this FC is actually going to be w over tan theta is equal to mv squared over r. We're going to express that w as mg. So this is mg over tan theta is equal to mv squared over r. Cancel out the m's, because that's what we don't know. We don't know g. G is going to be 9.81, so we do know that. And now what we need to do is we need to make we the subject. We're supposed to find we. So I believe this is just going to be we is equal to g r over tan theta, and you take the square to the other side, becomes the square root. And I think now you just have to solve for this. So this is going to be square root 9.81 times the radius, which is going to be 0.14 meters, divided by tan 28. So let's do that. Let's do that and see the answer we're going to get. So this is 9.81 times 0.14 divided by tan 28, and we just got the answer. It's equal to 1.61 meters per second. Okay, I think that's it for this question.